Part 2, mapping soil availability spatially and temporarily across farms. Worked in the case studies of Geordie Wilksch. My apologies, Geordie. I've spelt Geordie wrong there. And Dan Adams' farm. The guiding principles are that the method needs to be consistently applied across farms in EP. Covariates should be publicly available. Output scale should be consistent with decision making, and this scale I did the analysis at 30-meter grid size, and it's applicable to a place like the EP where, to be honest with you, it is data poor in terms of other covariates that are available. 4 phases. We go through soil sampling, we do soil analysis, we map the AWC, so we analyze and predict AWC from the soil samples. We map the AWC across the landscape, and then we temporally extrapolate soil moisture across the landscape. So soil sampling, we need to take account of the soils on the farm, and using a similar process as I guess in a way, the hypercube, we can use k-means clustering to identify the range of covariates, and within those relating to cluster those, and because they're covariates, we make the assumption that clusters represent a sameness of soils, and then we sample across those, so we make sure we allocate according to the area of each cluster a number of sites. In proportion to the area of the clusters. We then go in and we core to 1 meter. We subdivide into 10 centimeter increments. We plan for 25 for each of the farms. We achieve 22 for each of the farms, and that's not a bad outcome. Also, Jake was performing periodic soil moisture sampling at fixed sites across the farm at on various dates. Back in the lab, we analyze soil properties, say clay pH, for example, and we use that to make preliminary water retention estimates using Soil Water Express. We also did proper water retention using suction and pressure plates for the 44 samples or profiles that were collected. And we, at 10 centimeter increments, got layer AWC, and then we summed those for whole of profile AWC. And the graphs above my head give an indication of what 8 of those that we achieved for Dan's property. The mapping, we use digital soil mapping technique, applies computer machine learning to map soil properties, implemented in a publicly available GUI to reduce the user barriers using DSM tools. We built the models from the AWC data that we collected in the labs at the intersected with the covariate stacks, and the models apply covariates to create farm AWC estimate maps. We mapped AWC across the farms at 10 centimeter increments. We summed those for whole of profile to 1 meter, and we tested the reliability of those maps as well against lab data. Next phase, we gather soil probe moisture time series. We applied the corrections, so we have volumetric water. We convert, and then we convert, and we normalize the time series. So on date D, let's say, we take the probe signal from date D, subtract the minimum from the time series, minimum value, and then we divide that by the range, and the normalization, we get a value of 0 to 1. We apply that normalization according to the value on that date. So for example, the normalized value on date D, so say, is 0.7. So this is from Jake's data, time series data. No, my apologies. No, from the date D is taken from the time series. We And we have an AWC value at location A of 100 millimeters. Then by multiplying the 0.7 normalized value to the 100 millimeters of available water capacity, we get volumetric water estimation of 70 at site A, position A on date D. And we compare that data and test it against the DSM. Outputs. So the first phase, the sampling phase, we generated 4 clusters using k-means. My apologies, and the distribution of the estimated soil water expressed data at 1 meter profiles in each of those clusters at the sampling sites shows that there's a reasonable spread of sites in terms of AWC. Yeah. So apart from site cluster 4, which is these lower lying areas in the landscape, we've got a reasonable spread of sites in terms of AWC. The sampling design that we generated from that is represented by the red dots, so the 22 sites that were actually achieved, and the white dots are Jake's periodic fixed position time series sampling. The AWC mapping, we're using the DSM for the Dan's farm. Each of these is a 10 centimeter slice of AWC. So we're getting deeper and deeper. So this is 0.10 centimeters, and this is 90 to 100 centimeters. And the big one here at the bottom is that summed across the whole profile for 1 meter. The model reliability is R-square of 0.35, and the Linz concordance is an estimation of the 1-to-1 relationship. Those models are actually quite strong in DSM terms. What we did next was we took the lab AWC whole of profile data. So that's the value of the upper limit and lower limit, and we plotted that against the DSM profiles. So this is from the DSM profile. So red is from the DSM, and the blue lines are from the lab data. Now we see that the DSM has very much generalized the down profile spread. But in total, say if we take DA3, if you total the total AWC from the blue line and the red line, they would be roughly about the same. However, we've got some glaring variance where the DSM has over predicted the AWC. If we're taking, and we should do, we'll take the lab AWC as to validate against. The distribution, so when all these points intersected at 10 centimeters across the whole of that landscape with the DSM mapping, we get a very poor relationship. So the DSM hasn't predicted at those depths very well. Remember previously I told you the model quality, and that doesn't necessarily mean reality. It just tells you how good the model has predicted. Next, we take the probe signal, and that's the red line here, and then for 3 dates, and then we apply across those. So these are dates that Jake did his sampling, and we use the modifiers according to the normalized data. We applied that normalized data to the AWC from the mapping, and we plot the distribution across there. So each of these colors are from the relationship from the different dates, and we get quite a weak relationship here. So what we're saying is it hasn't performed very well at predicting across at those various dates the AWC using Jake's data as validation. Wilksch, I can go through these faster. Wilksch, we found that there was a 3 cluster solution The clusters distribute reasonably well. Remember, we're interested in the median data. There's certainly good split in the blue part of the landscape, or the blue cluster occupying the lower part of the landscape. The green areas are the flanking hillside, and the red areas are the sort of upper slopes. From that, we generated the survey design shown here. Black dots are where we surveyed, where we sampled, and the orange dots are where Jake did his periodic sampling. The DSM looks like this. Again, a slice for each layer, 0 to 10 here, all the way through to 92 to 100. And this is the total profile predicted across the Wilksch landscape in terms of AWC. Model reliability is pretty strong. R-square of 4.2 and a LINS of 5.8. So that's saying the model has done well, but that doesn't necessarily mean to see the reality. The prediction has been done well. Looking down those profiles, so using the DSM depth slices, drill down and at those sampling sites, W1, W2, and comparing the lab plate data, by and large, I think we're getting, even though the red, which is the DSM prediction, through the depth profile, is significantly generalizing the lab data, I think what we're seeing here is if we total these values, they're closer. Even this one, it seems to be predicting better. And indeed, when we plot these depths against each other, the predicted versus the lab, we're getting a pretty strong R-square of 0.48. Call it 0.5. So it's the reality is it's predicting quite well. Now we take the signal from the probe, FRSW, down at that front paddock, and we apply that normalized correction. This time for the dates, we've got 4 dates here, and we find that normalization process and then predicting for each of those dates, the DSM, so applying that normalization for each of those dates, and then testing against the field sample AWC and the predicted AWC, DSM AWC, we're actually getting a strong relationship. So the story is different here for some reason on the Wilksch property. So we're predicting across time using the signal from the probe better for Geordie's farm than Dan's. To wrap up, AWC is mapped using 10 centimeter increments for the whole farms. DSM has been publicly enabled by public data sets, covariates, and we use the DSM tools, which is available for users to reduce the learning curve for anyone who wants to apply this method. We've mapped AWC across the landscape at 30-meter resolution, and that's a scale kind of consistent with helping to make farm decisions. It's not operational, tactical scale, but it's sufficient to get a broad understanding of the moisture dynamics across the farm. The probe data, I think we've shown, particularly with Geordie's, that the probe data can be used to predict time-specific AWC across the farm, and that clearly means there's possibility of linking these systems live. So all you need is the AWC map. You need to generate that, and then temporally you just apply the signal as that's coming out of the probe at that time for the whole profile, I should say. Adams, the model did reasonably well, but the moisture extrapolation was poor. Wilksch, the model did generally better, and for some reason soil moisture extrapolation was much stronger. DSM reliability is driven by the quality of the model and training data. Here we use that AWC data. So we use that lab data as a gospel honest truth that is right. We can review that. And also the quality of the covariates. How well do those covariates predict across that landscape? And again, like the other components of the work, it's written up in a couple of reports that should be available to everyone. I'd like to finally acknowledge Christine Ratcliffe, Ross Searle and Brendan Malone of CSIRO for their support and advice through those two studies that I talked about. Amanda Cook, who's kindly been available and answering questions when needed. And obviously Geordie, who I spelt right this time I think, and Dan for their tolerance of us working on the farms.